let's take a look at maximum minimum problems, otherwise called optimization problems. Now, to do these questions, we really should review our graphing because it's really the same theory. And review that graphing, you can have different types of stationary points, but we're not interested in all stationary points right now. We're just going to be focusing on this type and this type. So this is called a maximum, and this is called a minimum. Now, graphically, you can see that if you were to draw the tangent to these lines, they're horizontal. So we know that a maximum needs to have the first derivative to equal 0. And similarly, a minimum needs to have the first derivative equal to 0. Now, if the first derivative is 0, that doesn't mean it's a max or a min necessarily. It could also be a horizontal point of inflection, which we don't care about here, but that's another possibility. So we need to actually show it's a maximum or a minimum. And there are two ways to do so. One way to do that, so to determine if it's a max min or even a horizontal point of inflection. One is to, well, basically use the sort of first derivative around that point. Or the second way to do it is to use the second derivative. So remembering that the second derivative, you both sound familiar with the first one, so I won't really go over that again. But the second derivative, remember, represents what?
The gradient of the tangent?
No, that's the first derivative.
Why am I confused? Okay. Yes, never mind.
So the second derivative represents?
Did you hear what I said?
No, I didn't.
Oh, concavity.
It refers to concavity. So here, this is concave up or down?
Down.
Right. And if it's concave down, then second derivative is positive or negative?
Negative.
Correct. So therefore, if you have a stationary point and it's concave down, which means the second derivative is negative, then that would mean that it's a maximum. Now, if it's a minimum, is it concave up or down?
Up.
Which therefore means the second derivative would be?
Positive.
Exactly. So this is the other way. So this is just a review of your curve sketching, but it will be very useful and exactly the same theory, basically, as what we're going to be using now for the questions in this section. So they treat it as a new sort of section, but really the theory is exactly the same. So if we're using first and second derivatives, then we're saying that the first derivative equals 0. That tells you you've got a stationary point, which could be any of these three possibilities. But we want a maximum or a minimum. We're trying to find a maximum or a minimum, which therefore means we've got two options. Method one is to sub in a few more points in the first derivative around the point. As I said, you both seem comfortable with that, so I won't go over that part. But the second way, which I usually prefer as well, is to go for the second derivative. And if the second derivative is positive, that indicates concave up, which means it's a minimum. If it's negative, that indicates concave down, which is a maximum. And therefore, this is really what you'll be using going forward for this section. Does that make sense?
Yes.
Great. All right. So the thing is, for the questions we're doing now, we're no longer technically graphing. I mean, really, mathematically, there's not a huge difference, but, we can graph it out if we'd like, but as far as the question's concerned, we don't really graph. So I'll show you what I mean. So this is not a perfect diagram, but good enough for our purposes, probably. So imagine that all four squares are the same. And we're basically saying that we're going to imagine that this is a piece of, aluminium or something. And we cut out these sections. Now we're told that the aluminium has dimensions, before you cut it, 40 centimeters by 25 centimeters. And we cut out 4 squares. So we're saying that all 4 squares are identical. And then you fold it up to form a container without a lid. You guys all understand what we're doing here? Like as in the description here?
Yep.
All right. So then the question is, I mean, you can probably see, right? I can change the size of how I'm allowed to change how much I cut out. So if I cut out a very, 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 very small square, what type of sort of container do I make? If I cut out a very small square.
One with very short sides lengths.
Which side length are you talking about would be small?
The height lengths. The height
Yeah.
lengths.
So if I cut out a very small square, just to give you an idea, I'll rub this out in a moment, but I'm going to look kind of something like this, right? I mean, that's the sort of idea, right? They're all going to just fold up very, very, very. Well, in fact, technically, there's no lid, so it wouldn't quite look like that. It would look more like this. But anyway,
We get it. Don't worry. Don't worry.
All right. It'll get a bit taller, right? Something like that. But what if I cut out like a very, very, very big square, like as big as I could almost make it? What happens if I, make the squares really big, almost as big as I could cut it, kind of like that?
You'd make a very ridiculous looking container.
Yeah, right? Well, I mean, it's not necessarily ridiculous. Sometimes you want containers like that, but you were telling me the first one has a very low height and it's sort of, very flat. What do you think this one would look like?
Very high height.
Yeah, essentially, right? So if it would still work out, essentially I would make one it would go towards this sort of idea, right? Does that make sense? Now, would these have the same volume as each other? Would number 1 and number 2 and number 3, would they have the same volume as each other? No, right? So because they don't have the volume as each other, we might want to just go, you know what? I've only got this amount of aluminium, but I want to make a container that can hold as much as, as I can make with this sort of idea. Does that make sense? So we basically want to find the maximum sort of volume
Oh, this is fun.
I can make the container have. And, determine, the size of the squares I would cut. And of course, the container in the end. Does everyone understand what we're trying to do here?
Yes, in theory.
Yeah. So basically, we've got this sort of situation. That's the question. And as we said, it's basically, we've got these sort of extreme examples over here. And we're basically going to just try and work them out. All right. So you can probably guess that, I mean, you know, if we go too flat, there's not much volume, like it's just too flat, right? And if we go too tall, well, the base is just too small, right? So it won't hold much volume, right? So you can probably guess it's kind of somewhere in the middle-ish, yeah? And so to do these questions, what I think you guys might have a bit more trouble with is how to start these questions. Now, some of these questions will have a bit more lead through than others. By the time you get to an exam, which could very well ask a question like this or very similar, you know, you might not be led through it as much. But basically the basic steps are, you know, you need to sort of read the question. So I'll just go over the basic steps here. We need to read the question. Let me do it on a new sheet. Ooh, okay. So in general, the steps that you need to be involved are to read the question and understand what's going on. Sounds very obvious, but you'd be surprised at how often you don't seem to be addressing what the question's asking for. Make sure you understand sort of the concept, the rules, the conditions. Now, once you've sort of understood all of that, then you basically need to ultimately find what you want to find. So in this case, you know, what you want to find, or what you want to optimize, I suppose. So in our example, volume, as a formula in terms of what we are varying. So, you know, we have something that changes the volume of our container because we're changing something. And in this case, that's the side length of our square. So remember derivatives, I mean, you can probably see where this is heading, but derivatives always involve something that's changing because you're changing something. So we're no longer talking about y and x, but it's still the same idea. We understand that in our question here, depending on how big our square is cut out, which depends on the side length of the square, it will affect, well, the shape and dimensions of the box, which will therefore ultimately affect the volume, which is what we want here, right? We want the volume. So you need to, you know, as a part of part one, you need to understand what you're trying to optimize and what you're changing. Is everything here clear?
Yes.
All right. Now, this may be very easy to you, or it may not, this step 2. But in case it isn't easy, I'm going to break it down into a few steps. And some questions are easier than others. So that means you would need to set the, you know, objective as a, you know, as a letter. So our objective is volume. So let's just give it capital B. You know, you would need to let the variable be a letter. So this is basically, you know, all your basic algebra things from primary, well, junior high school, I suppose. So let the variable be a letter. So in other words, what's our variable here?
The
What are we
square
changing?
size.
It'd be more specific than that. What do you mean by size?
The area.
Well, is there an easier
The
thing?
length and the width.
Yeah, the side length, right? So you need to be as, you know, you can't, if you say size, you probably mean area, but that's a bit harder to work with in general. So it's a side length of the square. All right. And then C is, again, you know, try to do step 2. Basically, you need to get, so basically we're saying we need v as a function of x, all right? So we've set v, we've now set x, and you basically need to sort of consider, you know, basic formulas. And, you know, information in step 1. So basically now you need to use sort of, you know, primary school maths and just your general math skills to get v in terms of x. And so this may, you know, this may be easy or hard, but that, you know, think about this, right? So we're doing a volume. If we're doing volume, what type of shape do we have when we make it into a box? What
Sorry,
sort of,
cut out. What did you say?
what type of, so, you know, we want to find volume, right? But to find volume, you have to consider, you know, the object you've got. What type of object do we have once we, you know, fold it up?
An open box.
Yeah, mathematically, how would you describe it?
A prism.
It is. What type of prism? You're on the right track. I just need you to be more specific.
Rectangular.
Yeah, it's a rectangular prism. Good. So it's a rectangular prism. So you can see that basically you're trying to work out the volume of a rectangular prism. Does that make sense?
Mm.
Now, you know, these just now start depending on the question, but I'm just wanting to show you how you would think about it, right? So if all of this comes very naturally to you, that's great. And this will probably be boring you, but a lot of students have trouble with this. And I think you guys might need a bit more lead through. So just consider it step by step. You know, what are we trying to work out? We're trying to work out v, including x. Well, start with thinking what v is. V is the volume. If we're looking at volume, and these are kind of question specific, but if we're looking at volume, volume of what? Well, volume of the box. Well, what's the box? In this case, it's a rectangular prism. And how do I work out the volume of a rectangular prism? Any rectangular prism.
Length times width times height.
Right. I'll just call it L times W times H here. But yeah, right? And so now, your job, if you like, is, do we know the length, width, and height directly?
No.
So I suppose what I'm trying to get at is, your job in step 2 is to get v in terms of x. Now, I could have just told you that and left it there, but you know, we want to find volume in terms of x. How do we do that? Well, firstly, set v, set your variable. Consider how you would find volume in the first place. As you said, it's length times width times height. And so now, if we don't know length, width, and height, then our next step here, if you like, and this again depends on your question, is find these in terms of x. Does that make sense? So
Yeah.
to find v in terms of x, you understand what v is made up of, in this case, length, width, and height. Then your job is now to you know, make x in terms of length, width, and height. And so I think it's now time for us to look at this question in diagrammatically. What can you guys see that this length here is x? And this length here is x?
Yep.
Now, do we know the dimensions of our, you know, our aluminium material?
40 by 25.
Right. So assuming it's to scale, this here will be 25 centimeters, and this here will be 40 centimeters. Does that make sense? And if you think about it, when we fold this up, what would it look like? You can either, you don't have to draw it out, but I'm trying to sort of draw it out to help you. Once we fold it up, it depends on what x is, obviously, but what kind of thing would it look like? Kind of like that, right?
Right.
And what would the height be then?
X.
What would this length be?
40 minus 2x.
And what would this length be?
25 minus 2x.
Very good. So recognizing that, you know, all those things are labeled, this being our, you know, width will be 25 minus 2x. This being our width would be 40 minus 2x, and so on. Right. So essentially we've done our job, right? We've now got, in this particular instance, we've got L must equal 40 minus 2x. Our width must equal 25 minus 2x. Now height must equal x. Does that make sense? And so at the end of all of that, which by the way, you could kind of do a bit faster. You don't have to write everything out the way I've done it, but I'm just kind of showing you what's sort of the thinking involved here. Essentially at the end of all of that, we have at this point done step 2. So V is, I guess, you know, x times 40 minus 2x times 25 minus 2x. Do you see what I mean by step 2 now?
Yes.
So at this point, we've got what we wanted to optimize volume in terms of x. Now you could expand it, and we probably will, or you might not, but that's not, whether you expand or not, that's really not a point. That's really up to you, depending on the question. But the point is, at this point, we have volume in terms of x, and that is key for step 2. And these steps might change a little bit, but the general idea is still the same, all right? Now, if I had not led you through that, I just want to know, would you have trouble with step 2? Or do you think step 2 is fine for you?
Yeah, step 2 is fine.
All right. Well, that's great, because step 2 is generally where I think most people have trouble with it, with the question. If you're fine with step 2, then the rest is really easy. All right. Because the rest is, you know, now that we have, you know, V in terms of X, you know, what we want to optimize volume in terms of the variable, the side length, we just optimize it. So that is here, maximize. And so step 3 is just simply going to be very simple using our calculus. So we want a maximum. So what do we require? First derivative to equal 0 and the second derivative to be negative. So basically, depending on the question, but your step 3 is then basically, you know, find the first derivative and, you know, B, if you like, solve for, you know, f dash x to equal 0. And then step 4, you know, find, you know, prove it is the optimal. So maximum or minimum, depending on the question. Either, you know, either subpoints in first derivative or second derivative. All right. And that should be enough. Step 5, you know, which I'm going to skip because usually not tested, applies if step 4 doesn't work or doesn't give you the answer you want. But it's usually not tested in SL, so I'll leave that. But, you know, just putting in a final step here, basically make sure you answer the question. All right, lots of students, go through all of this and get all of it right, but they don't actually answer the question. So, they might have worked out X, they might have shown it's, a first root is 0, they might have shown it's a maximum, but they didn't actually answer the question, right? Because the question might say, work out the volume of the container, or give me the dimensions of the container. Now, telling them X doesn't tell you the answer. You need to actually answer the question. Did you specifically answer what was asked? All right, so you can basically see the general steps here then. So in very broad terms, the first thing is you need to actually find the formula, all right? And a lot of students struggle with that. If you're saying you don't have trouble with that, then that's great, because that's just basically, that's nothing to do with calculus. That's just your general math skills, year 10 and earlier, right? If you're fine with that, then great. Once you find the formula, depending on the question, then to maximize it, well, it's just your calculus. First derivative is 0, and solve and all that. And second derivative needs to be negative for maximum, or if you're trying to minimize it in a different question, positive for the second derivative. Does that make sense in terms of the general gist of how you do these questions?
Yeah, makes sense.
So then let's actually finish this question off. So the question here requires us, we've already got up to the point where b equals x, 40 minus 2x, 25 minus 2x. For my purposes, I'll probably expand here. So it's going to be 1000 minus what? 130x plus 4x squared. Right? Does that all look okay?
Yeah.
All right. Then, so that's our v. Then your v dash is just going to be the derivative. Does that look okay? Okay. Now remember, your aim is to let this equal 0, which means we're really solving for 3x squared minus 65x plus 250 equals 0. Well, let's see if we can factorize it. Yep. So all right, so that should be 5, 3x squared minus 15. Yeah. So that means x must equal 50 over 3, or x equals 5. Does that make sense?
Oh, yeah.
All right. So we've got two answers here. Now, we could kind of just forge ahead blindly and kind of, figure out what's happening here. I'll do that first, all right? I'll do that first. But before I do that, are there any questions with what I've done so far?
No.
All right. So let me imagine I don't know which one the right answer is, because, I mean, I'll come back to it later, all right? Now, even if you know what the right answer is at this point, you do still need to do some working to show us the right answer. I'm going to proceed with doing it by the second derivative method. And I'm just going to imagine both these answers are still valid for the moment. And I'll find the second derivative. And if I do the second derivative, then I'll get 24x minus 260. All right. And then I'll sub in the value of 5, which will then be negative 140, which is negative. And I'll sub in the value of 50 over 3 times 24, which is positive 140, which is positive. So because the first derivative equals 0, but it's negative, what does that tell me about 5? First derivative is 0, but this is negative, so it's a
minimum.
negative. Negative means concave.
Down.
Concave down means?
It's negative. Wait. It's
What
the
type
minimum.
of point? Concave down.
Oh, maximum.
Okay. On the other hand, this one on the right ends up having the first derivative is 0, the second derivative is positive, which then means it's a minimum. Which means for max volume, x must equal 5. Now, if x equals 5, that means the length is going to be 30. I mean, depends on what the question's asked for, but that means the length would equal 30, the width would equal 15, and the height would equal 5. And the volume, if they asked for it, would be, 30 times 15 times 5, which would be 2250 cubic centimeters. Make sure, you actually answer the question and put in units if appropriate.
All right. Very cool.
Any questions with what I've done so far?
None.
So let's go back and dot a few I's and cross a few T's. So technically, I suppose over here, when I said let X be the side length of the square, dotting a few I's and putting it, I mean, I really should have said, it's the, in centimeters. I should have added that. Right? Now, you'll notice that, the theory basically is the same as your curve sketching. So we're really just using that because there's really no reason why I can't graph out this function except this on the y and x being x, right? So it's the same idea, really. Now, think about this. We said this is a minimum, right? Now, let me ask you, when x equals 15 over 3, right? This is, 16 and 2/3, right? So it's a bit over 16, yeah? Happy with that?
Yep.
Now, we worked out blindly, we went ahead and worked out that that's a minimum, right?
Mm-hmm.
And so we know it's not the answer we want, and that's true. But I want you to think about this, right? If x is 16 and a bit, doesn't make sense. I mean, we know it's not the answer we want. We know that for sure already.
Yeah, it doesn't make sense. Oh,
Why not?
because isn't it supposed to be 25 minus 2x? And then
Yes.
2x
We're
is
trying to cut out two squares, and this length is 25, right? So if we cut out 16 and 16, well, how do we get the two squares to overlap, right? That doesn't physically make sense. Does that make sense?
Yeah.
Which means really, what's the biggest that x could be in this example here? What's the maximum size that could make x, where it still sort of makes sense?
X has to be less than 25 over 2.
Right. We'll go less than or equal to. Equal to kind of just means you cut out, kind of, but just
Cut it out, you can't make.
And what's the smallest it could be?
25 over 2.
No, that's the biggest it could be. What's the smallest it could be?
But you can't make a prism when you cut it off the end.
Yeah. Just, it doesn't matter if you put the equals there. I mean, but that's what's the smallest it could be.
Anything greater than 0.
Yes. So basically, there's a domain for x. given the constraint of the problem, and that's what I mean by reading the question in part, that's part of what I include in step 1, but I didn't really point it out that much because, you know, especially in SL, it doesn't usually matter. That's part of the step 5 that I sort of glossed over here, but it's sort of inherent in your step 1, and, you know, it's explicit in the step 5 that I sort of mentioned, that I glossed over. But basically, in your question, when you read the question, you should also be considering, you know, like as far as the conditions, what is your domain of X in that question? Is there a values that it can't be, or that it has to be, and so on? Which therefore means, if we identify this when we read the question, then that really means by the time you get to this point and you got that, you could have, instead of blindly gone ahead and, you know, got rid of it, you could have at this point simply said, X can't equal that because it's not in domain. Does that make sense? We could have simply got rid of that answer at that point in time already. We don't need to actually work out the second derivative because we know it can't be right.
Yes.
And even if we worked out the second derivatives for both of them, and both of them, you know, were negative. In other words, you know, if you didn't know what was going on, you would go, hey, there's 2 maximums. Even if this one did work out to be a maximum, you would still need to get rid of it because it doesn't make sense, even if it was a maximum, right? Are we clear on that?
Yes.
Okay. Now in SL, they usually don't try to trick you too much. So usually those sort of things don't happen. They also usually won't do things like, hey, we want a maximum, but you don't find any maximums, and there's only minimums. That's when you use step 5, all right? That's when you do step 5. Usually SL, they don't really test that. So I've kind of glossed over that, but that's just kind of giving you the gist of it. All right, is everything clear?
As water.
All right, great. In which case then, let's take a look at some more example questions.